Okay, in the second talk, I will be also explaining basically how the logical categories work without mentioning case theory. And I want to start with this question. Let's say definition. So let's see the presentable stable category. Then let's just call it flat. If the tensor rank with C, consider the function from PRA stable to PRA stable, preserves fully phased functions. Yeah, and you can ask the very basic question like, is every presentable stable category flat? And this was actually a point of confusion and frustration for some people, I think including Dustin and Denise. And it wasn't clear like how to prove this or disprove this, but actually it turns out that there is a very nice criterion for this, like theorem that C is flat if and only if C is dualizable. One implication is quite obvious, like if direction is clear, just because if C is dualizable, then C tensor something is just the same as functors, canonical preserving functors from C dual. And this, of course, preserves fully faithful functions. But much more interesting is the only direction, and first I'm going to explain this. Basically, the main observation is the following. First, notation. Let's denote by presentable, accessible, stable. So this will be infinity two categories. Actually, this will be the only time when I will mention infinity two categories. So most of the time we'll be talking about infinity one category, but here infinity two categories. So this is infinity two category of presentable stable categories and accessible object functors. I should write bigger, sorry. I'll try. And accessible exact functors. And let's just ignore set theory for now. I mean, you can take care of set theory just by imposing conditions that they are kappa presentable and the functors preserve kappa compact objects, but for now, let's just ignore this. It turns out that there is surprising additional structure, like on presentable categories, like for any C. Let's say here. Consider it as an object in PRA, but I claim that there exists a natural O-plus to functor. C tensor something from PR accessible to PR accessible, which extends the usual Lorentz tensor products from PRA to PRA. Now I'm also considering PRA as a two category, PRA stable. So this is like the first statement. And second is that if C is flat, then this is actually a actual two functor. So not only a plus, but we get an actual two functor. And so to construct this Oblast functor.
So can you remind me what oplex means? I know roughly what.
Roughly what I mean is that C tensor composition of two one morphisms maps to C tensor F composed with C tensor G with all the compatibility conditions. And for the unit, there will be no problems because unit is continuous, so unit will go to unit. Sorry, for the identity functor, there will be no problems. Yeah, so the issue will be that in general, this is not an isomorphism. Okay, so let's describe this Oblast functor on the level of one morphisms. So basically, like assume that C is kappa presentable, and have some accessible exact function from D to E. But by default, all the functors will be exact. So suppose that we have some accessible functor. Then we can just define the C tensor F as a composition. So we go from C tensor D. So this is just the same as kappa left exact functors from C kappa opposite to D. Kappa left exact means commutation with kappa small limits. This is just always the same thing. And now we can compose with F, and we go to all functors, well, let's say all exact functors, from C kappa opposite to E. And then we apply the functor which is left adjoint to the inclusion. So this is left adjoint to the inclusion. Is some issue with the yeah, we get a couple left exact functors from C kappa opposite to E, which is just the same as C tensor E. And with the description, you can see why we get a priori only Oblast functor, because we apply this left adjoint to the inclusion. So when we take the composition, we will not literally get the composition, but only comparison map. Yeah, but and this is in fact sufficient already to rigorously define this Oblast functor. You can just figure out in terms of complete single space objects in infinity one categories. Yeah. So this construction essentially defines this Oblast functor, but it's just not clear at all why flatness would imply that it's an actual functor. And to see this, I will give you alternative exposition. Yeah, so let's make an observation. That for presentable stable T and E, we have equivalence of categories. So this accessible functors from D to E, again accessible exact functors, they're just the same as what I like to call correspondences between D and E. And this is like, this is just, we define it as the category of triples with T, I0 and I1, where I0 from D to T is fully faithful, and also I1 from E to T also fully faithful, and fully faithful continuous functors. And we have a semi-orthogonal decomposition. So T has a semi-orthogonal decomposition into I1 of E and I0 of T. So as usual, semi-orthogonal decomposition means that there are no homes from right to left, and this case will generate this subcase generates the ambient case. And basically this equivalence, if you have some object in the case of correspondences, it just goes to a composition of I1 right adjoint with I0. And in the other direction, it's basically semi-orthogonal gluing. So if you in that direction, if you have a functor f, then you can associate this category, which I like to denote like E semi-orthogonally glued with D using f. I mean, this is basically a Black's limit of this arrow. So I mean, if you're familiar this Black's limits and limits, if you consider small categories, then there is a nice observation by Efimov that the four categories are all equivalent. Like all Black's limit and colimit, you have 2 times 2, which is 4 options, and all of them are the same category. But here it's convenient to use the Black's limit description. So these are like triples x in E, y in D, and the map from x to f of y. Yeah, so this is the same. So these two categories are just equivalent. It's quite straightforward to check. And now we can describe this functor C tensor correspondences. C tensor something from correspondences from D to E to correspondences from C tensor D to C tensor E. And this is very simple. Just take C I0 and I1 to C tensor T, C tensor I0, C tensor I1. And it is quite a formal exercise to check that this is a well-defined object in this case of correspondences, because like one of these functors has a left adjoint, another has a continuous right adjoint, and so when you multiply by C, it still holds, and semi-orthogonality also holds because it can be expressed in terms of vanishing of the composition of functors. So basically, you still get an object of the case of correspondences after tensor. And now, well, let me give a vague explanation why flatness of C implies that we get an actual two functor. Now, first, like we have this equivalence between correspondences and accessible functors, and there's an initial question: what is the composition of accessible functors formulated in terms of correspondences? We want to understand what is this composition from, let's say, from D1 to D2, and D0 to D1, to correspondences from D0 to D2. And this is pretty straightforward. So we just take C12 here. Let me just animate these inclusions from the notation, so they're kind of assumed. So this case here with similar position into D1 and D2. And you take another object T23, and then the pair T01. Then this pair simply goes to the push out. To the certain subcategory T02 inside T012, where T012 is the push out, where you have embedding of D1 into both of these categories, and you take push out in the array. And this is full subcategory generated by the images of T0 and V2. So this is like the most natural thing which you can do, and it's actually gives you correct answer. So this the composition of correspondences is compatible with the composition of accessible functors. And again, this can be made exact in terms of complete single space objects.
So you can generate it in the
generated as a stable subcategories or equivalently generated by Kalinin's. This is the same thing because the categories are semi-orthogonal. If there are no homes in one direction, then generating by Kalinin's is the same thing as generated by finite elements, just by extensions. So in this, in either two ways, this will give the same answer. So this is the composition of hypothesis. Yeah. So it again has a similar composition into D0 and D2. Yeah, and yeah.
So here, way to get like tensor accessible function to C, here you put another way tensor accessible.
Yes, and they are the same.
They're the same.
Yes. Yeah.
So what was the question?
The two, I defined two ways essentially of tensoring accessible functor with C. One is written there, and another is use the correspondences and then go back to accessible functors. And these are the same; they are compatible.
So if I understand correctly, this is the first time we actually need stability.
Well, maybe, yeah. No, I think that to talk about semi-orthogonal doings, I mean, it would be not very convenient to do it without stability.
So everything so far doesn't require stability.
No, it does, it does. I mean, already for this equivalence, you couldn't, I think you cannot even properly formulate it without stability. So yeah, you need stability here. Yeah, so we have this composition of correspondences defined by using this push out. And now, let's understand what happens with after we tensor with C. So basically, tensoring with C commutes with all Kalinin's, in particular with push outs. In particular, C tensor T01. You take push out along C tensor T1, C tensor T12. This is just the same thing as taking C tensor with push out T01 and T12 along T1. It's just the same thing, but the problem is when we take the full subcategory generated by this T0 and T2, or by C tensor T0 and C tensor T2, then we have only the comparison function, namely, so here, so we have a functor from C tensor T02 to the full subcategory here, which is C tensor T01 composed with C tensor T12. And the only problem is that so this is not an equivalence in general. Because the functor from C tensor T02 to C tensor T012 is not doesn't have to be fully faithful. In general. But if C is flat, then it is fully and it follows that C tensor something gives you an actual functor from accessible stable categories to itself. Yeah, I was a little bit vague with two categories here because let me very briefly formalize this in terms of complete single space objects. So basically, here. So basically, this infinity two category of correspondences can be described as a fibration of a delta where the fiber over n is basically just disjoint union over all collections of n plus 1 presentable stable categories. I'm really ignoring this theory here. So, and I'm considering this as a set, not just as equivalence classes, but I mean I'm considering the set of all presentable stable categories. Of categories, let's denote them as correspondences D0, D1, etc. Dn. And this correspondences D0, D1, etc. Dn. This is basically the data of presentable stable category with inclusion of 0, etc. In, where ik is from dk to t, fully faithful continuous. And T has a similar orthogonal composition into In of Tn, etc., I0 of D0. And you have this condition which can be formulated like this, that if k plus 1 inside T is generated by the images of dk and dk plus 1, then I require that T is equivalent to the iterated push out, so we take T01, D1, T1, 2, and so on. T minus 1. And then this gives you a well-defined complete single space object in infinity one categories. So this gives you, yeah, I should put brackets somewhere. So this category here. And this gives you a well-defined complete single space object. I mean, you can figure out what are the maps between the fibers and check that this is Cartesian fibration. And then basically you get honest functors from C-tensor correspondences for D0, D1, Dn. Sorry, C-tensor something from this category to correspondences for C-tensor D0, etc., C-tensor Dn. And so you get a well-defined map of fibration over fibrations of categories over delta, but it doesn't necessarily preserve Cartesian edges. But again, if C is flat, then you can directly see that it preserves Cartesian edges. So that's kind of a rigorous way to do this. Yeah. So we get this.
Do you prove that this full infinity two category is equivalent to PRL stable accessible?
Yeah, you can PRL stable accessible. You can also describe it in terms of such fibration. You can just directly construct. Let me just keep it because it's pretty straightforward. Actually.
So just to double check, they're the T, like in the category T, you mean like the image of D has no non-trivial vortices to the image of E, right? Or is it the opposite?
Yeah. Homes in T from I0 of X to I1 of Y is 0.
Okay.
And they can together this image is related. Yeah. Okay, this is so this is like description of this two functor. So this gives you kind of a formal way to show that if C is flat, then we have an actual two functor. Now let's use this to deduce this only if direction, which is like flatness implies divisibility. So the argument is a little bit crazy, but you should expect it when you try to prove such a. So. Now we're proving that C is flat implies that C is localizable. Using this extra two functoriality. So recall that C is dualizable even only if 86 Großen direction 86 holds in C. So Thomas will, I think, explain this in some detail, but for now, let's just formulate. I just recall what this axiom is. So this is saying that for any collection of directed sets or feature space trace, but it doesn't matter. Let's say directed partial sets, Ki. Where I runs through some set of indices. So, you take some functors from Gi to C, where J I goes to X Gi. And you require that we have an isomer. So we can take the product of collisions of these functors. And we always have an echelon from the colimit over the product of this partial sets of products of this xgi. So you always get such a map, and we require that it is equivalence isomorphic. And now it might look weird, but it turns out that this extra functoriality allows you to deduce 86. So let's do it. So equivalent way to understand this 86 is the following. So we can take, first we can take a commutative square without any assumptions on C. We have a commutative square product of cases of functors from Ki to C. It goes to product of copies of C. The function is just the product of collinear functors. Now you have a case of functors from the product of Gi to C. And here we have a functor to C, also the collinear functor. So this is like a product. Let's call this C. And this is the product of collinear functors. This is the collinear functor. And now we have functor here, which is just whose components are just left-hand extensions. And you have a functor here, which is just the diagonal functor. And let's call it. Let's use some notation. This will be W E, let's say U. So this is just the diagonal. And this is like left-hand extensions, collection of left-hand extensions. So,
like fiber-wise coordinates.
well, left-hand extensions, yeah. Whatever it is, yeah. Well, left-hand extension. And tautologically, you have a commutative square, because if you just consider some components, some C, you can just compute this left-hand extension with just a collinear directly, or first compute left-hand extension to some GI, and then take the collinear. And now, 86 means that dual Chevalier condition holds. Condition holds, meaning that let's say W composed with V, with U right adjoint is equivalent to a V right adjoint composed with T, with this condition. And now, and this is a good sign because dual Chevalier condition is just some two categorical notion, and we have an actual two function. So now to deduce AB6 in C, you just so let's denote this square by star. Then we just see that star is just the same as C multiplied with same square for the Keterer spectrum. So we just replace C with the Keterer spectrum. And now, using the fact that C tensor something is a two-factor on this large category of accessible functors, and plus AB6 for the Keterer spectrum. So AB6 definitely holds for the Keterer spectrum. We deduce that ABC holds for C. So it becomes just it's a little bit crazy, yeah, I know, but I don't think that there is a more natural, maybe there is, but at least I'm not aware of a more natural way to prove this. Yeah, so this is so it's not surprising that this question was open, right? Okay, so this is yes. So this is about the surprising criterion of dolizability, sort of flatness. Yeah.
So a question, like, do we have any guess for the case when it's not stable because flatness is?
Yeah. Then I actually don't know if this holds. Yeah. It seems plausible, but at least this proof definitely doesn't work because I use this stability to identify it. Yeah. Yeah, it's a tricky question. I mean, maybe there is a counterexample, but again, I mean, for such questions, it's very difficult to construct them. Yeah, you can try. Yeah.
What about relative over some rigid category?
Over rigid, there is no problems, but I think that this should also hold over general. Well, let's even say even monoidal presentable stable category, but now you consider left modules, and there is notion to the dolizability, like there is a dual right module, and I think that flatness still should be equivalent to dolizability, but I mean the proof should be more tricky because you need to include this weighted limits and modification of AB6. I think it should work, but I just didn't figure out the details. Yeah. Okay, so now another general. I want to explain another general story about dolizable categories and also give some examples of non-dolizable categories, which is useful when you have some notions. Give examples of objects which don't satisfy perfectly. So we have this collection of dolizable categories inside presentable stable categories, and you can ask like another naive question: is it closed under extensions? And let's more specifically just consider a short exact sequence where you have extension of properly generated categories. So we have some functors f and g, and suppose it's a short exact sequence, and we assume that f and g are strongly continuous. And yes, you can ask the question, is it true that C is at least dualizable? And it turns out that the answer is no, and there is a precise criterion for this dualizability. So let's use some notation. So let's use the symbol GR for the right adjoint to G, and let's also take the twice right adjoint, GRR, right adjoint to GR, which exists because G is strongly continuous. And then, so we have this semi-topological addition of C into GR of int of B and F int of A. As we already discussed, such semi-topological decompositions are classified by functors by accessible functors from right to left. So so this is basically semi-orthogonal doing of int of B and int of A by a functor phi, where phi is composition should be G twice right adjoint to G composed with F. Sorry if I'm mistaken. Yeah, that's correct.
Sorry.
Yeah.
Maybe I missed something. Previously, your definition of strongly continuous is, it seems to me that you defined it for compactly assembled.
Yeah, but I didn't mention it, but for stable, in the stable case, it's just requiring that right adjoint can use with coordinates, which means that there is a twice right adjoint. Yeah. So we have this gluing functor, and now you can observe, well, almost tautologically, that accessible functors from int of A to int of B. This is the same as functors from B to pro of int of A up to taking opposites. Opposite. And yeah, and let's just denote the image of phi by psi. So psi from B to pro of int of A is so it's a functor which corresponds to our gluing function. And then you can prove the following statement that so with this notation, the following are equivalent. So first, that C is dualizable, that C is completely related, and that the essential image of psi, so psi, recall, psi is a functor from B to pro of int of A. The essential image of psi is contained in the category of Tate objects A. I think some people denote this category by L of A, but call it Tate objects to both call it like Lefschetz objects and Tate objects, because originally it's due to Lefschetz, but let's just avoid this confusion and denote by Tate of A. So this is this is just the so this is I wasn't complete. Stable subcategory of pro of int of A generated by pro of A and int of A. So this dualizability of category in the middle turns out to be equivalent to the fact that it's completely generated and equivalent to the condition that the image of this functor containing the case state objects. And corollary of this is that if you define this x1 from C to A as a space of short exact sequence of small categories of this form 0, A, let's say D, B. So this is a large space, but locally small, and this is actually equivalent to the space of functors from B to take objects of A. So you can understand what X1 is. And if you consider split extensions, then it is well known that depending on whether you take whether you assume the right adjoints or left adjoints for the short sequence, they correspond to functors going to pro phase or into phase. This is like gluing pro functors, yeah, whatever. This is like the usual stuff. So I mean, the fact that you can glue categories using functors to pro phase or into phase, this is well known, like when you just glue them semi-orthogonally. But for this short sequence, I don't think that this was known, like in any generality. So this seems to be kind of new description. And to see this, I mean, to prove this necessary and sufficient condition, you just need to use the very standard, very classical results of like Niemann and Thomason about like compact objects in quotients. And okay, well, let me briefly sketch this. Yeah.
There's no assumption in the proposition.
Yeah, no assumptions on.
Like the following are equivalent.
No, the following are equivalent. Like this is notation. I mean, I introduced some notation. Yeah, and for this C and C, A, B, and psi. So this is equivalent. The possibility of C is the same as generation, the same as the condition that the image of psi. Yeah. Okay, so the idea is basically that whenever you so we have this inclusion of C into compact objects of A into compact objects of C. Then if C is dualizable, then the quotient, when you take the quotient of C by end of A, and take compact objects, then this is the same as taking compact objects. The quotient of compact objects of C by A, and then taking Karoubi completion. And in particular, for any compact object in this quotient of C by end of A, there exists a compact object Y in C such that Y projects to X plus X shifted by 1. This is like the usual Thomason's theorem, which classifies Karoubi dense triangulated subcategories in triangulated categories. And already using this, you can see that 1 is equivalent to 2. So we reduce. Yeah.
Is TSR to the
Sorry?
the adequate completion?
Yeah, this is like Karoubi. Yeah, let's say adequate completion.
Thank you.
Yeah.
But this isn't Thompson, it's Thompson Trevaux.
Ah, okay, yeah.
The idea to do the Trevaux.
Yeah, that's true, yeah.
Historian has visited, he was dead for many years, he visited Thompson.
Yeah, I know, but somehow in the literature, I've only seen this reference to the Thomason's theory. Yeah, maybe I should correct this too. So we deduce that 1 is equivalent to 2. Basically because if C is dualizable, then we are already able to lift up to direct summas, we are able to lift all the compact objects here to compact objects in C. And so together with the objects of A, they will generate C. So basically 1 and 2 are equivalent. And then Okay, let me sketch the equivalence between 2 and 3. So basically, we want to be able to lift, again, up to direct summons, we want to be able to lift compact objects of B to compact objects, objects of B to compact objects of C. And we just observe the following, that for X in B, like the following are equivalent. So first is that there exists a lift Y, which is a compact object of C, which lifts X plus X shifted by 1. So this is equivalent to the following, that when we take psi of X, so psi of this function to prove into 3. When we take psi of X plus its shift by 1, then there exists an exact triangle or fiber sequence U to this direct sum. So V, so this is like fiber co-fiber, so let's say fiber sequence because the case is stable, such that U is contained in pro of A and V is contained in of A. Basically, this equivalence between 1 and 2 is just you're trying to lift this object to a compact object and to just write down what should be satisfied. So this to hope it's just just a direct computation. Yeah, but this is literally saying that so 2 literally means that psi of X plus its shifted by 1 is contained in this elementary take objects, which are we just take just stable subcases generated by profile and endofile, but you don't take retards. All such objects are extensions of an end object by a pro object. It's like the usual stuff, like you take compact lattice, like CP and QP. Yeah, you get this, but now applying, as Dustin recalls, Thomas and Rapport theorem, we get that condition 2 is basically equivalent to the condition that psi of X is a tate object. So the condition that this object plus its shift by 1 means such an exact triangle, it literally means that this object is a tate object. And so we learned that the ability to lift this compact objects up to direct summons to compact objects of C is just the same as requirement that the image of anything is contained in the tate subcategory program. Yeah. So you get this, I think, very nice criterion of the legibility of this category in the middle. And let me just give a couple of applications of this.
You're going to give some examples where it's satisfied with.
Well, yeah. First, I'll give a very simple example when this is satisfied because, well, as I mentioned, this so this functors to the tate category, they classify short exact sequences, and let's just consider some short exact sequence, for example, 0 to p-torsion abelian blocks, perfect complexes with p-torsion homology to perfect, so Z to perfect complexes over Z inverse. And then the corresponding z-linear counter, like this was like over the epsilon base, so it was just over the sphere spectrum, but you can do all the same over some ring. So the corresponding z-linear counter from perfect objects over Z p inverted to take objects of P-torsion perfect objects. Like you can guess what it is. It sends Z spin inverted to QP, where QP is considered as a take object in the usual way. So and similarly in general, when you have some algebraic array, some scheme, and it goes up there. It's similar description. But now let's discuss some examples when this condition is not satisfied. So in particular, that when this image is not contained in the state subcase ring, and so this case ring in the middle is not Euler. There is a very natural linear algebraic example for this, which is just you consider position that K be a field, and let C be the category of triples, like take V and W, which are just derived, which are just copies of vector spaces over K, and you take some map phi from countable direct sum of copies of P to countable direct sum of copies of W. Then basically you can direct computation shows that psi of K. So this is like some some pro vector space. This is simply the inverse limit, formal inverse limit of over functions, set-theoretic functions from natural numbers to itself, of direct sums over natural numbers of K to the f of n. And of course, the partial order is just point-wise in this partial set. And the transition maps are just projections, coordinate projections. And this is not a take object. So basically, if you just denote this guy by xf, then so we just need to show that the images of these guys in the completion of the Calvin category, okay, this is not pro-constant. This is equivalent to saying that this is not a take object. And this is quite easy to see because so if you just so we just use the fact that for f less equal to j, this conditional map is split surjective, split epimorphism. And so if we conclude that if this guys form pro-constant system in the Calvin category, then this must be eventually a constant system. So if you have some pro-system where transition maps are split epimorphism, split epimorphism, and if it's pro-constant, then it is essentially constant. Eventually constant. So it must stabilize. But this is obviously not the case. So this is not the case just because fiber of the map from f plus 1 to xf is just the countable dimensional vector space. So we win. We show that it's not a table. So particularly the case category is not always. And let me just formulate.
Does that mean winning or losing, right? You know, it's
No, I mean, we constructed a simple example of a non-dualizable categories. It's nice.
yeah.
Is it true that it's still only the one completely generated?
It is, yeah, but I mean, this is pretty simple. Yeah.
Nice.
Yeah.
So the question, like you didn't prove the equivalence of like little one and little two there, right? Or-
I didn't, but I just said that you should just prove this directly. You try to lift an object to a compact object, and you just see what should happen for this. That's equivalent. It's essentially a formulation. And let me just mention this classification of dualizable subcategories of classification shifts on a fine Nasserian scheme.
Also use the top black order.
Yeah. That's, yeah.
By the way, is there any like similar result which can characterize the expansion of two dualizable categories of two?
You just replace. I mean, there is a version of data category for the dualizable category. It's also subcategory in the pro completion of this category, but it's just slightly more tricky. I mean, you just get the statement. If for dualizable categories extension of C by D, this is like for functors, strongly continuous functors, let's say twice that joint functors from C to int of states, let's say continuous state of D. It's just more trickier, so I decided to restrict to completion rates of categories. Yeah. But yes, there is also a similar application. This is equivalence of spaces, of large spaces. Yeah. Okay, so let me finally mention this classification of. So we consider subcategories of derived category of commutative Nasserian ring. So we will consider like consider localizing subcategories of D of R, and this it is known. So there is a bijection between this set. So this is due to Niemann and subsets of spectrum of R. So basically, S subset S goes to, we can denote this by D sub S of R, and this is just it is generated by residue fields. By the residue fields of this prime ideals, and Niemann also showed that the inclusion is strongly continuous if and only if S is closed under specialization. And in this case, it's completely generated category. And now, it turns out that, I mean, using this general criterion for this exact sequences, you can prove the following, that the following are equivalent for a subset of R. That first, that ds of R is dualizable, and that S is convex. Which means basically if you have some specialization, so if x specializes to y, and y specializes to z, and x and z are in S, then y is also in S. In particular, you get quite a lot of examples of non-realizable categories. You just take any non-convex subset. Also let's mention that this is just this is also equivalent to the condition that this is completely generated. But this is kind of easier to see that if S is convex, then this category is completely generated. So example. Again, let K be a field. Take C to be the full subcategory of specification shifts on the affine plane. So drive category of polynomials in X and Y, which is formed by modules such that when you invert X and mod out by Y, you get 0. And then C is not realizable. So this category is like so C is like quasi-coherent shifts on affine plane minus a copy of GM, which is like x equals 0, y and y is non-zero. Unless I'm confusing x and y, sorry. So this is, of course, doesn't make sense because this is not an algebraic variety, it's not a scheme, but like you can still try to define quasi-coherent shifts in terms of the kernel of the fallback to this GM, and this category is not realizable. And this is just a special case of this general criterion. Okay, I think I should stop because I'm.